Hello YouTube! Let's talk about velocity a bit more, and we had an initial definition of velocity that was just space divided by time, and that was quite interesting but not really complete, and today we want to complete that definition. So there were two things that were wrong with this definition. First, it couldn't apply for non-constant velocities, and the second one, it couldn't apply for initial conditions that weren't 0 seconds or 0 meters. And we have learned another definition, which was velocity is the slope of this line, which is delta x divided by delta t. And that also worked for initial conditions which weren't 0 seconds and 0 meters. So that was quite fine. And why am I talking about this? The answer is pretty simple, because when we use this formula, we can only calculate differences in space or differences in time. So if you want to say we have a velocity of 5 meters per second and we have a time difference of 10 seconds, we know that the velocity 5 meters per second times the time difference of 10 seconds is going to be 50 meters. But there's a big problem. It's only the difference that is 50 meters. We don't know where we are at all, because we only know we are 50 meters further. But further from where? It's only a comparison to an unknown point. So that's a problem. But we can help this problem. We just use the definition of what delta x and delta t actually are. Delta x is some arbitrary value 2 minus some arbitrary value 1, and that from space, here x2 minus x1, and from time, t2 minus t1, whereas x and t2 have to belong together and x and t1 have to belong together. So we can also do that for not only some arbitrary values, but also for our initial values and the total values. We say total x and total t and total and initial x and initial t. So the difference between total x and initial x divided by the total t minus the initial t. That is also the velocity, because of the definition of velocity. Now, this formula, v is equal to x minus x0 divided to t minus t0, that formula we can form around a bit, and we get x and t if we want to. So x is, for example, x is equal to v times t minus t0 plus x0. We could also get t out of this formula. T would just be x minus x0 divided through v plus t0. We could get both x and t from this formula, the total x and the total t, and v. So we have all three values again, which is exactly what we want. All three values. Velocity, space, and time. That's all we want. So there was another problem, which was that our velocity still has to be constant. Now let's see what happens if we don't say it has to be constant. And we use the definition, velocity is the slope of the spatial function. And that is a good definition, and that works even when we don't have a constant velocity anymore. Delta x divided through delta t doesn't work, but the definition, the derivative of the spatial function still works. And we're going to look at how exactly that works. Let's see first why the delta x divided by delta t doesn't work anymore. Let's look at this example where we have a non-constant velocity. The velocity here is negative x values, we go down, and positive t values, we go to the right. So if we divide them, we have a negative velocity that's smaller than 0. And here we go to the right and up. So we have positive x coordinates and positive t coordinates. That's the velocity that's positive. So the velocity is not constant anymore, and we can't use delta x divided by delta t anymore. That's the problem now. So why is that a problem? That's two different points, and at two different points, of course, we have two different velocities if the velocity isn't constant. But now let's look at this one point, and we're going to see that at this one point we can get two different velocities by using delta x divided through delta t. And that's a problem, because at one point we can only have one velocity. So we can calculate the velocity, the normal velocity, just by dividing a certain delta x through a certain delta t. Now let's take also this pink triangle here, this pink slope triangle. So we say the velocity is also, well, we have taken half of the time here, or I have taken half of the time here. So it's 1/2 delta t. And as you can see, it's not really 1/2 of the delta x, but it's more like 1/3 of the delta x. So what we get here now is this isn't really exactly v anymore, this isn't exactly the velocity anymore, but instead is 2/3 of the velocity. So we get a smaller velocity at the same point. At the same point we get a smaller velocity. So this is a big problem, because even though we measured at the same point, we still get a different velocity, which means that this delta x divided through delta t can't apply for constant, can only apply for constant velocities and can't apply for inconstant velocities. What do we use for inconstant velocities? Well, we use the definition velocity is space divided through time, a bit more formal, a bit more physical. Delta x and delta t only applies for the slope of a line. If you want a general slope, we use the derivative, as I aforementioned it. If we use the derivative, we get this definition. Right here, this definition. This definition is the definition of velocity, which is quite common. Velocity is the derivative in respect to time of the spatial coordinates. For example, we have about an x here that is sinus of t plus 1, just about, and if we derive that, we get cosinus of t. So cosine of t, sine of t plus 1, derivative is cosine of t. Now there's one big problem here, because what is the cosine of 1 second? What is the cosine of 3 seconds? We don't know, because it doesn't exist. Only exist is the cosine of some value without a unit. What we forgot here is scaling again. So as we scaled up here and we said, oh, the x compares to 1 meter as 100 times, or x compares to x0 as 2 times, we also have to say, well, the time really isn't total in here in this scene. It's time divided through t0. And we also have to care about the other units. Well, I made an example here, an example for some spatial function which uses the correct units. That's one thing you have to pay attention to. So this uses the correct units now and always works. That's something you have sometimes pay attention to in physics, even though you might not want to, but sometimes you have to. If you now calculate the velocity, you get the velocity is cosine of t divided through t0 times 3 meter. That's what you expect. But you also get times 1 divided through 1 over t0. That's because of the chain rule. We have to take the inner derivative of t divided through t0 and write it right here. So now we have a problem. There's an additional unit. We have meters, and there's also 1 over t0, which is 1 over second. That's problematic, isn't it? And the answer is no, it is not problematic. Because that's just what we want. We don't want the unit meter anymore. We want meter over second. That's the unit of velocity. So by deriving, we get the right unit. And that's something we have to remember. And that's something that always should happen. By deriving, you should always get the right unit. If you don't get the right unit when you derive your formula, you have either used the wrong formula, or derived wrongly, or just messed up counting your units. But in the end, you should always have the right units. That's like almost definition of it. So by deriving any function, you should get the right unit right here. You should get, for example, 3 meters per 2 seconds, which is 1.5 meters per second. Now, this definition is well, and this definition is good, but this definition is not the final definition. There's something more that we can do, which is now we can only move in the x direction, but what if we want to move in the y and z direction too? And now we get to the last definition, which is the velocity is the derivative with respect to time of the vector of our spatial function, the spatial function vector. If we do it with vectors, we are perfectly fine, and this is the real definition. By the way, the derivative in respect to time in physics often is also a dot about something, and if you derive it 2 times you get 2 dots, and if you derive it 3 times you get 3 dots. That's just a thing we physicists like to do. For example, we have circular moment. How do we derive that? Well, a vector you derive by simply deriving every component. So we have the uppermost component and we derive it, the middle component we derive it, and the lower component and we derive it. Pretty simple actually. For example, a times cosine of t divided through t0, we derive that cosine is minus sine. So we get minus a times sine of t through t0, and the chain rule also gives us divided through t0. And if we look at the units now, a is in units of meter, cosine has no units, so this is meters. t0 is in units of time, a is in units of meters, so we have meters per second. This has no unit, and a minus also has no unit, so this is in meters per second. As is this, and 0 is in meters per second and any other unit you want it to be in. Now, one interesting thing about this vector, the special vector, is a special thing that its length is actually always the same. And this is something very special. The velocity seems to not change. It's always the same. The length of this vector is always the same. But what changes is its direction. And now we get to a point where with vectors, there's not only the length of the vector, the speed we have, but also the direction in which we have the speed. And 2 parts of velocity: the speed we have, the norm of the vector, and the direction of our vector, where we are actually going. That we have these 2 parts now is what causes that when we want to move in a circular fashion, we actually have to apply a force that goes inward. That's because we are not really changing the norm of the vector, we are not changing the length of the vector, but we are changing the vector because we are changing the direction. And that's the explanation for the acceleration you need in rotation. We are going to talk about rotation a lot more, so don't worry, this isn't final, this isn't all I have to say about rotation, but it's a little fun teaser I can give you right now. There's one other thing we haven't discussed, which is we know now how to calculate the velocity by deriving, but we haven't talked about how to get the time or the space with this inconsistent velocities. Now that's pretty simple. If we have an inconsistent velocity, then we just have to do the opposite of deriving. Instead of multiplying with t, what we did before, we multiply with dt, which is called integrating. We do the opposite of deriving, which is integrating. So we integrate over the velocity function to get our spatial function. Our x function is an integration over our velocity. And we start from our t0, go to our t, and we integrate over our velocity function. Now one interesting thing is, if we substitute t0 right here, then we have the integral from t0 to t0, and that's all 0. And we have x is equal to 0. But wait a moment, at t0, we shouldn't be at 0. We should be at our initial condition. So one last thing we have to add here is the plus x0 that we have to add here. So this is the final formula for our initial conditions and inconsistent velocity. We integrate over, with respect to time, over the velocity function and add the x0 at the end. Now this right here is a variable. You don't substitute any value for it, you leave it as a variable, while this one you substitute a value for, this one you substitute a value for, this x0, and you substitute a whole function for this v. What you get in the end is following: an x of t function that has in it some arbitrary mathematical functions like the e function, the sine function, the cosine function, whatever. But in those functions is a t, and the two initial conditions t0 and x0. And if you want the time now instead of the place, you just take the formula and put the values a bit round, multiply by something, divide by something, and you cut by something, and so on, and so on, and so on. And then you just have, you're left with t is equal to some function of x of t of t0 and of x0. So that's what you're left with then, after you sorted this function here around. So now we can not only get the space, the absolute space, we can get the absolute time, and we can get the velocity. So now we are complete again with our triangle. So we have three different formulas we are going to use, or to be more precisely, even four. The first one is velocity is space divided through time, which is just for constant velocities and no initial conditions. If we add initial conditions, we use this one. Velocity is delta x over delta t. And of course, by our little trick I showed you, we can also get the absolute x and the absolute t out of that strange formula. Now, when we want to talk about an inconsistent velocity, we have to use the derivative, either the normal derivative with respect to time, or we use the vector derivative with respect to time, which is just the same just for all components. And when we do that, we can still get the velocity, but we can also get the total space and the total time by simply reversing the derivation, the derivative, and integrating. We integrate with respect to t from our t0 to our variable t, and add the x0 at the end as a little constant we add. And we get that our x of t is some function of t and our initial conditions. We can sort that function around, and we can get the function for t, which is a function of our x of t and the initial conditions. So we can as well calculate our x with any given t as our t with any given x. And that's everything we wanted, actually. That's everything we wanted. So that's our last and final definition. And I'm going to hopefully see you again. And I hope you had fun with this lesson. And see you next time, everyone. Goodbye.